All right, let's talk about more torsional strain. And this time we're going to do an example with a molecule a little bit more complex than ethane, propane, or butane. Those are the typical examples that you see in organic chem textbooks. But let's branch out a little bit from that and see how we can utilize the knowledge of the eclipse conformation energies, the gauche conformation energies in relation to the stagger. And for this molecule, since there is not a lot of equivalency, you really have to specify which carbons you're going through. And what that ultimately means is that you have to make sure to name the molecule correctly. So this molecule in particular has the following number scheme. So this is carbon 1, that's carbon 2, that's carbon 3, 4, and 5, meaning that this is 3-methyl 2-phenyl pentane. That's the name of the molecule, right? So we're using this number scheme for the correct name of this molecule. And here I can tell you to basically draw a Newman projection from any which single bond that I want. So in particular, I'm going to choose to look at this thing from the perspective of carbon 3 to carbon 2. And the first carbon that is being labeled or named got to be the front of the Newman projection. The second one, by default, is going to be the back portion of the molecule. So you don't necessarily need to go in this exact order, carbon 2 to carbon 3. You could go backwards. It's really up to me. But you're going to have to base it on the proper numbering scheme for the name of the organic molecule. So we're going to look at this from C3 to C2. And what that means is that the point of view is going to be from the right portion of the molecule. Now the other thing I'm going to do, notice here, I'm going to change things a little bit. This is a methyl group, that's a methyl group, and technically this whole thing here is an ethyl group, right? That's worth 2 carbons. And I'm doing this to basically simplify the molecule into just the point of view of carbon 3 to carbon 2. All right, so now what we're going to do is look at the point of view. Once again, we're going from carbon 3 to carbon 2. Carbon 3 is going to be the front, and we have one thing above and 2 things below on the front carbon. On the back carbon, we have 2 things above and 1 thing below. And notice here that I'm actually going out of my way to draw out the hydrogens that normally are not present in the bond line structures. And just to pinpoint this one more time, whenever you see the bold bonds present for a carbon-carbon bond, automatically you ought to think, okay, well, to complete the octet of this carbon, you need to have a hydrogen. And if this bond is bold, the carbon-hydrogen bond is going to have to be dashed. And over here, if the carbon-carbon bond is dashed and you need to put a hydrogen to complete the octet of this central carbon, then the hydrogen carbon bond is going to have to be bold, right? And that's what we're seeing right here. We have bold hydrogen and we have dash hydrogen on the back. All right, now looking at this one more time. So this is meant to be C2 to C3. On top we have 1 bond above, 2 bonds below, right? So that means that you're going to have a Y down on the front. Ethyl is on top, hydrogen is on the bottom, and so is methyl. But it's also important that you keep that point of view. The hydrogen is pointing towards the front of the screen, but from this point of view, it's technically looking like it's on the left side of the molecule. The methyl group here is going to the inside of the screen, but from this point of view, to you, it looks like it's on the right side. So be careful about where you position these things. If you change that, that could affect your overall analysis. Now on the back portion, from the point of view, which is the carbon 3 to carbon 2 bond, you have 2 things above and 1 thing below. So on the back, you're going to have your Y up structure. And as I was saying, since this is the point of view, anything that's pointing to the front or towards you from the screen, to you is going to look being on the left side of the Newman projection. Anything that's going inside of the screen from this point of view, right, so from right to left, is going to look to you as if it's going to the right. And anything that's, you know, a regular bond is going to be simply going either down or up, right? In this case, we're below the carbon 3 to carbon 2 single bond, so you're going to have the phenyl group pointing down. All right. So what we are basically going to determine is what are the energies of all the different conformations as we rotate clockwise or counterclockwise. And what I want to point out right now is that one simple way to go about it is to, on the bottom portion right here, simply draw all the different stagger or gauche conformations. And notice that this is the one that I start with, the one that we just determined here. Ethyl on top, hydrogen on the left side, and methyl on the right side, which is this molecule right here. Keeping the back the same in all of them, all I do is rotate the front clockwise or counterclockwise. And so the ethyl, and this time I do 120-degree separations, so, or rotations, so that the ethyl ends up always in between, never on top for the bottom Newman projection. So ethyl is between methyl and hydrogen. Going clockwise will have you now place the ethyl group between the hydrogen and phenyl, which is what we have on this structure on the right side. And rotating that by 120 degrees, we'll have now the ethyl group be between the methyl and the phenyl. This is going clockwise, right? So that's what we have right here on the farmost portion of the diagram. Going counterclockwise from the point of view of the original staggered conformation or the original Newman projection, we have now the methyl rotating counterclockwise to be positioned up here between methyl and hydrogen, as we see in this structure. And if we continue doing that one more time counterclockwise, the methyl group will now be between methyl and phenyl. And you just make sure to do that for the other two groups of the front portion of the molecule so that everything is in the correct place. All right. Up here, on the other hand, you're going to have all the eclipse conformations, regular as well as total eclipse. And you simply want to start in the correct order. If you go counterclockwise, the ethyl group will be above the back methyl group, as we see right here on the structure. If we go clockwise, we're going to have the ethyl group be on top of the hydrogen group, as we do see on this structure here. Continue doing the rotations 120 degrees. So if we go clockwise on the structure, the ethyl group will then be on top of the phenyl group, as we see here. That methyl group will now be on top of the other methyl group on the back, as also observed here, and the hydrogen will be on top of the other hydrogen. So this is going clockwise. Do another 120 rotation. The red methyl is going to be on top of the black hydrogen. The red hydrogen is going to be on top of the phenyl group, and the ethyl group will be on top of the methyl group, as you can see on this structure over here. Likewise, taking the original Newman projection, rotating 60 degrees to end up with the eclipse conformation, places the ethyl group on top of the black methyl, red hydrogen on top of the phenyl, and the red methyl on top of the black hydrogen, as we see over here. Rotate those structures 120 degrees, methyl goes onto methyl, ethyl goes onto phenyl, hydrogen goes onto hydrogen, as you can see over here. Rotate that 120 degrees in a counterclockwise fashion, methyl will go onto phenyl, ethyl will go onto hydrogen, and hydrogen will go onto methyl, which will get you to this structure over here. All right, so with that analysis, what's basically left to be done is to look at the energies of each one of these conformations. And we're going to start with the stagger or gauche conformations altogether. All right, so, oh, and one more thing I should probably point out to you, calling this structure stagger is a bit of a misnomer, because technically speaking, until we find out which ones have the lower energy, we really won't know which one is truly the stagger one. So ideally, this is the one, but we're about to find out. So what I'm presenting right here is the gauche conformations, excuse me, the gauche conformations for um, the interactions of the neighboring groups. And we have hydrogen on hydrogen, hydrogen on methyl, hydrogen on ethyl, hydrogen on phenyl, which are all possibilities for the different structures, Newman projections down here. And then we have the methyl on methyl, methyl on ethyl, methyl on phenyl, ethyl on phenyl, which could be interactions happening as well. So let's start with these two. The thing I want you to notice is that these two structures are basically the same ones, right? in fact, there's no difference. They are identical, right? Red hydrogen is on top, red methyl is on the left, red ethyl is on the right, and that's exactly what we have right here. And the back, of course, is the same in all of them. So these two structures are the same. So what we need to do is basically look at the interaction in between. You have methyl next to hydrogen, you have hydrogen next to hydrogen, you have hydrogen next to ethyl, you have ethyl next to phenyl, and you have phenyl next to methyl. So we're gonna, oh, and of course you have methyl on methyl. So we're gonna look at each one of those interactions. I'm highlighting them here in, keeping them in color, either blue, red, or pink. And we simply add them all up, right? So hydrogen on hydrogen, that's worth 0 strain energy in the gauche or staggered conformations. Hydrogen on methyl, same idea, it's worth no energy. So hydrogen on methyl and hydrogen on hydrogen is worth zeros, which are the two numbers you see here. Then the hydrogen on ethyl is worth 0.42, and we see that right there, hydrogen on ethyl. We also have methyl on methyl, right, which is a total of 3.3. We also have the ethyl on hydrogen, right, which is the 0.42, already talked about that. We have ethyl on phenyl, which is total of 6.3, so that's right here. And we have the methyl on phenyl, which is worth 5.9. So these are all the values right here. You should have 6 values altogether when you consider the gauche or staggered conformations. When you add them together, you find out that the values are 15.9. So this is how much higher they are in energy if you compare them to Newman projections that would only have hydrogens in every single one of the 6 categories. All right, so now looking at the structures right here, notice that once again methyl is on top, ethyl is on the left, hydrogen is on the right, and that's true for the structure on the very end right there. So these two are basically the same structure. So we do the same thing. We have methyl on methyl, that's one interaction. Methyl on hydrogen, that's another. Hydrogen on hydrogen, hydrogen on phenyl, phenyl on ethyl, ethyl on methyl. So we add up each one of those interactions by inputting the correct value, right? Hydrogen on hydrogen is 0, hydrogen on methyl is also 0. Hydrogen on phenyl is going to be 0.84, methyl on methyl, methyl on ethyl, and ethyl on phenyl, you use the corresponding values. And you add them all together to get you 14.2 value for the total energy. And what we're now finding out is that this gauge conformation is actually lower in energy than the gauge conformation on the far end, at least on the left side, right? The last one we need to investigate is the staggered conformation over here. And for this conformation, we do have ethyl next to methyl, methyl next to hydrogen, hydrogen next to phenyl, phenyl next to methyl, methyl next to hydrogen. So the methyl hydrogen interactions, those are worth 0, right? And there's 2 of those, so that's 0 and 0. Ethyl on hydrogen, however, is worth 0.42. Hydrogen on phenyl is worth 0.84, so we're introducing those values now. We also have methyl next to ethyl and methyl next to phenyl, which are worth 3.8 and 5.9. So add all those values together and you find out that this is worth 11 kilojoules per mole. And this is by pure luck, by the way. This is actually the lowest energy value for all of them. So this is indeed the reference point or the lowest energy point for all the conformations that we have on the bottom. Now we're going to do the same type of analysis, but this time for the eclipse conformations. And these are actually a little bit easier because you only have to consider 3 things. You have the interaction of hydrogen on top of methyl, hydrogen on top of methyl, or methyl on top of phenyl. There's only 3 things you need to consider. And if we look at the values for the eclipse conformations, which are all higher than the ones for the gauche or staggered conformation, we do a similar thing in terms of analysis. We notice that these 2 boxed molecules are the same conformations, right? Hydrogen on left, ethyl on right, methyl on the bottom, on the front portion of the molecule. So what we do is we recognize what it is that we have. And what we have is hydrogen on top of methyl, methyl on top of phenyl, ethyl on top of hydrogen. So we have these 3 specific values to play with. And we simply add them up together. It's just those 3. So the eclipse ones are actually a little bit easier to handle, right? So the entire value once added is equal to 25.1. So that's the value we get here. And you might have noticed this is substantially higher than the values we got for the gauche conformations. Now the two right here, methyl on methyl, hydrogen on hydrogen, ethyl on phenyl, these two conformations are the same ones. So we highlight those specific interactions, hydrogen on hydrogen, methyl on methyl, and ethyl on phenyl, and we add them up. And we find out that those structures have a value of 30.6, which is also higher than any of the gauche conformations. All right, so then we get to these other two, which are equivalent. We have ethyl on methyl, methyl on hydrogen, hydrogen on phenyl. So we highlight those specific interactions. We add the values together and we find out that these conformations have a value of 23.8. So these are actually the lower end energy values for the eclipse conformation. But regardless, if you compare your gauge conformations to the eclipses, none of the gauge conformations ever go higher than even the lower eclipse conformations. And this will be true every single time that you do torsional strain analysis on your Newman projections. So all of the eclipses should be above, all of the gauge conformations should be below. And then the last thing you need to do is just kind of relatively raise the energies, right? The higher the value, the higher up you should be in terms of the vertical axis. And the lower the value for the eclipse conformations is, the farther down you should be. So in essence, if we, relatively speaking, apply that frame of work, then the energies for each conformation should look roughly like this, right? So notice that 23.8 slightly below 25.1, 30.6 is the one that's highest above, and then we have a similar profile for the gauge slash staggered conformations. So all you have to do now to complete the entire energy diagram is, for all of the conformations below, simply turn this line that I have drawn for the energy into a concave up shape. And for the eclipse conformations, turn that regular horizontal line into a concave down structure. Specifically, do what I just show you right here. So concave up for the bottom structures, concave down for the upper structures. And all that's left to be done is to simply connect the ends to each other. And once you do that, you got yourself your energy profile for your molecules. Now, ideally, you want to, once you determine the energies of this, if you need to rearrange things, I would do so. I personally like it when the low energy conformation out of all the gauge conformations is the one in the middle. So you might need to play around a little bit, um, with those numbers until you get this lower energy Newman projection in the middle. You know, call it Malcolm, right? Malcolm in the middle. Anyway, so this kind of represents the entire setup for the entire structure, and you don't need to introduce the little circles showing the rotations necessarily, but it's just to give you perspective. Everything to the right of the staggered conformation is going clockwise. Anything to the left of the staggered conformation is going counterclockwise. Okay, so in the next video, we're going to talk about the torsional strain that is present in cyclohexane. So see you then.